Okay, this is a review session for the midterm. What I want to do today is just outline the topics which are covered, talk about what the topical areas of the questions are, and maybe point you to some resources that might be useful for you. I'll try and keep it brief so that the equations that we talk about are the full set that you need to be able to complete the test. But that doesn't mean you might not go to look at background information which is available in the book and also online to be able to make sure that you really do understand all those key concepts. The other materials that are available to you, I think, are in the past. If you go to the course resources page, then ultimately this review will be posted here. It'll be 30 minutes, I'd imagine. You can look at the previous reviews. There are also some PDF notes of what you might look at as well, generically for this area of the class, that kind of encapsulate the concepts. But the best way, I think, to study, if you're looking for ways to do that, will be to look at this review session, to concentrate on the things that we discuss, and to go and find background information on that material. So the material, this is really on fluid dynamics, which was the Bernoulli equation. You remember that 4.1 was really static acceleration, and that's kind of excluded here. But 4 and 5 are Bernoulli equation, both normal and long streamlines. Conservation of mass is control volumes and concepts of moving control volumes, deforming and moving control volumes, and static control volumes. And conservation of momentum, which is Bernoulli's equation, basically written in a generic framework. And so those are the topical areas. Those are the materials that are appropriate both for the scheduled midterm and any conflict exam. Specific to the scheduled exam, the 3 questions deal with fluid pressures normal to streamlines, where we go across streamlines and we look at the fluid pressure distribution. Bernoulli equation applied along streamlines, including head losses, and also where cavitation comes into the calculation, and also conservation of linear momentum that includes some rudimentary conservation of mass and also manometry. So we'll talk about each of those components and put together the equations that you might need to have at your fingertips to be able to deal with them. So let's deal with the first ones first, manometry. So manometry is the science, if you like, of measuring pressures. We've done some examples in class with U-tubes and the proverbial U-tubes, etc., etc. And so if I can just do this. And so the principal characteristics, what we'd like to do is be able to move from pressure at one location to the pressure at a second location, and typically to do that we need to remember the rules that describe that behavior. We know if we go down we add pressures, and that pressure should be equal to the change in height multiplied by the unit weight of the fluid. We know that if we go up we reduce pressures. We know if we go across simply connected in the same fluid to the same elevation, we end up with the same pressures. So P, I guess, dP dx equals 0, I guess is the establishment of that. We know that if we're in a gas, then the unit weight of the gas is much less than the unit weight of a liquid, and therefore we can typically ignore that unit weight. And if we find ourselves in a closed container with the trapped fluid, then that is the vapor pressure of that fluid. And we can always quote vapor pressures in either absolute pressures or gauge pressures, and we have to be sure which one it is that we're using if we're doing that. And so if we're using so atmospheric pressure at gauge pressure is 0, and absolute pressure is something like 101 kilopascals. I guess the other component is that if you're looking at flow within a moving stream, then it matters exactly where you might measure that flow. And so if you're measuring it in a standpipe, then if you measure the flow here at point 1, then it would have some velocity attached to it. If you measure it right at the tip of a pitot tube, then in that particular case the velocity, because of stagnation, would go to 0. And so you have to be careful where you're measuring these as to what magnitudes of pressure that you might choose to use. So be careful with that. The second component might be Bernoulli. We know that Bernoulli is written along a stream tube of some form. The velocities typically, are in the direction of the stream tube, and so they're along the stream tube. And that stream tube would have cross-sectional areas attached to it, which we can use. And if we write Bernoulli, we know that we can write it in terms of the pressure head, the velocity head, the elevation head, and that has to be equal to upstream and downstream alike between the two of them. Oops, that's 2. And the elevation head, plus any head losses that we have in the system. And so in this, I suppose, if we have too many unknowns, what we can do is we can try and close the set of equations by writing continuity, by noting, for instance, that A1 V1 is equal to A2 V2 from this geometry. This is the continuity expression. And what we want to be able to do is to have only one unknown in this equation to be able to solve for it. We can think of these as magnitudes, these components here being equal to magnitudes of what we've called the energy grade line, which is perhaps an important concept for what we have been talking about. And if we draw this energy grade line, what we would find is if you draw something that's constant, so the fact that these are equal to each other means that the magnitude of the energy grade is constant. So if there's a head loss within the system, what that physically means is that you go from the upstream to the downstream. So I guess this is along the length of the stream tube. This magnitude here would be the head loss. This would just be a horizontal line, and this would be the magnitude of the EGL. And this is just equal to a fancy way of saying that this has to be equal to the sum of elevation plus pressure head plus velocity head. And this is constant along the length of it. And so the only way that this will change is if you move downstream and you have some extra component here that subtracts from that. So if there's a head loss in the system, then the magnitudes of the sum of these will diminish as you go along the length of it, and it's reasonable to assume that it changes linearly as you go along the length of it. If you're going along a stream tube which happens to be horizontal and it's the same cross-sectional area, then clearly neither of these two can change, and so that change along the length of it has to be purely manifest as the pressure. Okay, so that's Bernoulli, which is parallel to streamline, Bernoulli, which is perpendicular to the flow. Remember that the flow velocities are in the direction of the streamline. Normal to that, there is zero velocity by definition. So the velocities that we're talking about in Bernoulli that's perpendicular to streamline is always in the direction of the streamline. And the expression that we have for that is if we think of this streamline, which is this, which has attached to it some radius, and according to this it has, oops, not that, two locations, and we look at those locations in terms of the depth as they go into this. Then what we need to do is we can write the equation that describes the pressure, the velocity head term, and the elevation head term. I guess they're not heads because they're not units of length, and that is always constant. So in the same way as we did for Bernoulli, we can write this out at two particular points, points 1 and points 2. And we can use that to write this out as a longer expression that includes both sides. But if, for instance, we wanted to calculate the pressure distribution between this location here and here, then what we can do is we know that it will look something like this. If this is the free surface here, then this pressure has to be 0, and that the pressure change normally would be equal to the unit weight times the depth that you go down here. This is h in this particular direction, so we know what the pressure buildup is. But the net effect of, and that would be given by just going through the fluid according to using these expressions here. But if we're going across a streamline, we have this extra term, which is really the centripetal acceleration, which means that the velocity of the fluid is changing because it's changing direction. And so we have to accommodate this term. So what we need to remember in terms of this is that the magnitude of z is always positive upwards. The magnitude of n is always positive, actually no, sorry, the other way around, is always positive into the center of rotation. So this is positive n, this is positive z. The velocity is always this streamline velocity, which is always, we take as an average across the flow. And if we have this, then we can write this both at point 1 and point 2. We can rearrange that to get the magnitude of the pressure change if we change elevation. And if we do that, we'll get exactly this expression here if we ignore this centripetal term. And including this centripetal term requires that we integrate it from this point here to this point here. And maybe you should look online to see how we've done that. The net influence of that is that, not surprisingly, if you have flow that is going across that's attempting to go on this trajectory, but it's being forced to go in the velocity of the streamline, then this angular acceleration that we get makes it feel as if we're lighter. And so what you'd physically expect is that if you drew the pressure distribution below this, not unlike this here, then this would be the pressure is equal to unit weight times h, h being the distance that you go down here from the free surface where the pressure has to be 0. And if the acceleration is lessening gravity, then we'd expect that the change in gravitational pressure with depth would be this amount here. And this amount here is exactly due to this expression. Conversely, if the flow trajectory was like this, then instead of going horizontally, this is the streamline velocity Vs. This now is being accelerated upwards. In being accelerated upwards, it's the same as going up in an elevator, and the magnitude of the pressure distribution with depth would look like this. And this also is this term. And the reason that the magnitude of this changes is because the direction of this vector in towards the center of rotation has now changed direction relative to z. Z is always positive upwards, but this value of n has changed. And so the sign on this integral has changed, and therefore the distribution changes. So that would be something that's, I think, useful to review also. And we certainly did an example in class. Maybe, I don't recall exactly, maybe it was 4.3 or in 5. You can check that out. If we look at conservation equations, we looked at two. We looked at mass conservation. And I suppose, we've always used this little diagram to define the behaviors as a system. If we look at the behaviors because of, I'll do it there, the outward normal to this, and some velocities that are going both into the system and out of the system, then we can simply write the mass conservation equations as m dot plus rho volume change plus volume times density change are equal to 0. Important that we know the sign conventions that increasing volume, so volume increases, that's positive. If density increases, that is also positive. And the mass flow rate is going to be equal to the velocity times the area times the density of the fluid that's going into the system. I guess these are all summations. And the sign convention on mass flow rates is that if it's out of the volume, then this is positive because it's the dot product of the normal vector and the velocity. And if it's into the volume, then it's negative. So we have to be careful about the sign convention that we use in this particular case. Sometimes we can write this for a moving control volume as equal to the mass flow rate is equal to density times area times the relative velocity relative to the boundary of the system. And we've always explained this relative velocity in terms of looking at a static observer, where if we draw the hose that is pushing fluid out at some velocity w, that the boat is moving at some velocity of the control surface, then relative to a static observer, we see the fluid moving at the sum of these two vectors. And so we can always use this expression to represent that behavior. And if we need to get this, then we define the relative velocity across the boundary in terms of the static control volume velocity, but also how quickly that control volume is moving. So that's how we deal with that. And finally, if we look at conservation of momentum, Then again, the expression, we work on this similar control volume, same idea as before. We have an outward normal. We have flow velocities that come across this boundary at the downstream, I guess, and the upstream. And areas for each of these. Then the expression that we have to define this is going to be equal to sum of the forces is equal to the relative velocity relative to the boundary multiplied by the mass flow rates. And I guess this is also a summation. There are 3 of these equations, but typically you only need to deal with one at a time, and that is that the force in the x direction would be equivalent to the sum of the velocities in the x direction multiplied by mass flow rates. So that simplifies things a little bit. This relationship for defining mass velocities relative to the boundary applies here also. And likewise, when we use a moving boundary, we have to accommodate it in this expression here. And so if we do that, then what we can do, clearly, if the control surface is not moving, then this magnitude is just equal to the static impinging velocity. And if it is moving, then we have to rearrange it in terms of the magnitude of W is just going to be equal to the static velocity minus the velocity of the control surface. And these are vector components. So this is a positive vector. In the opposite direction would be a negative vector. So these are a vector sum to be able to do that. Anything else we need to do? No. You need to be able to draw a free body diagram. Oh, I guess the sign convention is useful. And so when we look at this term of W multiplied by the mass flow rate, then when we look at the mass flow rate, then just as before, when we dealt with this, the definitions of the sign convention for the mass flow rate is it's positive if it's out of the volume and it's negative if it's into the volume. But the magnitude of the velocity is always relative to the Cartesian coordinate system. And so in this particular case, this would be positive. And this one also, because it's in the same direction, is also positive. So again, we have to be careful of the sign convention. And I think that is the full set of expressions that you need to know how to use to be able to thrive in this particular test.